So welcome back, everyone. I'm so we're we're recording now the second part of this lecture. Was the fourth lecture in the class on principal component analysis or on so dimensional reduction, where this one is covering principal component analysis and multidimensional scaling. I pretty much finished the principal component analysis section. I want to make a couple of quick notes, and then we'll mostly cover the multidimensional scaling part in this class. The first lecture was interrupted because there was a 20-minute power outage on campus. So we are back in my office. You can finally see my face after all these lectures so far in a mask. So great. So I want to make first one more note on the difference before we move on to multidimensional scaling. There was a question I was answering when the power went out about the difference between PCA and regression. And we had talked about how PCA is unsupervised and regression is supervised. But there's kind of one other geometric point I was thinking to make in this, right? We're in a high dimensional space, and we think of having some data in this space, right? So these are possibly these data points. Think of A1, A2, and so forth. And we can generically think of, well, we're fitting some linear subspace through here, and so both of these. Well, so one difference is with PCA. If this is AI, you are projecting onto B of AI, and then you're measuring the residual in this way, where if you are, this is for PCA, whereas in linear regression, there is a specific Y direction, right? And so the residual, instead, I'm getting an AI hat, right? This is like and I think of this as, I should actually think of this as AI Y, but there's a special Y quirk. The response variable, the dependent variable, is special, and I'm trying to predict AI Y hat, where Y hat is the value on the model, but the X value, right? There's this, X1, X2 now. The AI lives in this lower dimensional. In the regression case, there's a lower dimensional plane here, right? And so the X data lies in this plane, right? And so I'm not changing that. I'm only changing the Y data, and I'm making an approximation Y hat now, which keeps the same X value, which is multidimensional, but has a different Y value. The other difference we're thinking about is in PCA, then B is going to be rank K, where K is often much less than D, than the dimensionality of everything that's going on here. But it's still it's not necessarily a one-dimensional subspace. Okay, it could be one or two, but one dimension is reasonable. It can be actually a line in here. Okay, what's different in the regression is regression, at least in linear regression, I have a function from RD up to R, which is Y. Okay, so I mean, sometimes you map to multiple dimensions. We won't talk about that in this class, but it's a function, which means that for every value a in two dimensions in this case, it maps to a different value in the y-dimensional space. So that means I don't really ever have a line in the my model is never a line up there unless it is about a unless this line is unless my d dimension, my x dimension is only one dimension as well. So this model I'm fitting here is actually going to be the same dimensional space. It's kind of cutting the space into two parts, right? It's always one dimension lower than the d plus one dimension for y, right? If I include y, I'm in d plus one dimensions, and this model is kind of slicing this into two parts, right? There's above and below, and the residual has a sign in that way. So, and that's another way that these are kind of different from each other. Sure. So, okay, great, good. I'm starting to get some people in the audience now, which is good. Another thing I wanted to show you was just quickly, there was a demo in Python that again is linked off the webpage for PCA. And I just want to quickly go through centering. Centering will show up in multidimensional scaling. So if you're watching for that, you'll want to see this, right? So I have a data matrix A with 3 data points and in 2 dimensions each, right? I've entered that. And I can compute the mean of each column here, right? The mean of the first column is 2. The average of 1, 2, and 3 is 2. And the mean of the second column is 6. The average of 3, 5, and 10 is 6, right? And so one way to center it is just to subtract, using this direct way of subtracting the outer products times this average, times C, right? So I'm getting this outer product matrix of all ones, which is a 3 by 3 matrix, n by n matrix, all one. I've subtracted that, and that's one way of doing the centering. The other way of doing the centering is creating this centering matrix C, right, which is this identity matrix. The identity matrix, you write EYE, right, as like your eyeball. That's how you generate a 3 by 3 identity matrix. And you get an all ones matrix that's by 3, and you divide this by n, which is 3, right? And this gives me this matrix. We can see it's along the diagonal. It's slightly less than 1, in this case 0.66, and it's negative everywhere off the diagonal, right? And if I multiply that C times A, I get A CC or A tilde I was showing in the previous part of this lecture. Then I've done the centering, right? And we can plot. If we plot the original data points A are in red, and the new ones are in blue. If you look at the blue, if you look where the 0, 0 is on this plot, you can see that the center is in like the average of all the blue parts, all the blue points. Okay, so the centering works, and I get the same result either way I compute this. Okay, so it's just a quick demo on centering. Okay, so let's get back to multidimensional scaling. Okay, so multidimensional scaling. This is MDS. Okay, and so this is meant to be an initial application of where that PCA and SVD and eigendecomposition, where these show up in other tasks that you do. This is going to be a case where this is still kind of an unsupervised task, where a lot of the cases it shows up in actually other supervised tasks where I have some labeled data, and the book will go into more detail on a couple of those, but there are many more places where it shows up. Okay, so the multidimensional scaling, let me describe kind of the basic setup here of what is going on. The input here is going to be a matrix D which is going to be in n by n. So it's an n by n matrix D, and this is a distance matrix. So I'll say it's a distance matrix. And I'm going to think of having n objects, let's call them, which I call them P1, P2, up to Pn. And I'm going to store Dij is going to be the distance between Pi, and Pj. Okay, there's some distance between them. Okay, and this is my input. It could be some sort of Euclidean distance. It could be kind of like one of these L1 distances we talked about, or it could be we're just presented this. It could be that this distance is actually not given as a matrix, but it's given as like a function, right? So think of these guys are different. So some cities, and then the distance. This is the cost of an so it's like an airplane ticket between city I and so city J, right? If I go to a website, Expedia or something, and I say, what's the cheapest cost to get from one city to another city? It's always going to charge me something, so it's positive, right? But this is not exactly the Euclidean distance between the cities. What if I want to say that's the real cost of going in between these cities, right? So I'm not given their locations, right? Maybe now what I want to do is I want to kind of embed them. I want to map these into a location, right? My goal is now so embedding of P1 through Pn into Rk, so that let's call this embedding map mu, so that if I compute the Euclidean distance between Pi minus Pj, that this is approximately the distance Pi Tj I've been given as the input, right? So the input I'm given is approximately the Euclidean distance after I construct this embedding, right? So I want to take this data where I'm only giving distances and I want to draw them on like a map. I want to plot them on a piece of paper. Okay, so I'm not given the original coordinates of the data points. I'm only giving the distances between them, and I want to somehow draw a picture, right? And so this comes up all the time in visualization. I might have some way of saying how similar are two data sets, two individuals. I construct some distance between them, and I want to kind of draw a picture to try and understand how things are grouped, right? Or to draw a figure for a paper, right? These are kind of yeah. So this is the goal, okay? And so I would like to compute. So to compute this, right? All right. So how do we compute this embedding so that I get these Euclidean distance? I'm going to use kind of these ideas from SVD and eigen decompositions to use the basis I get out, the best rank K basis, to give me the embedding of this data. Okay, but I don't quite have the right thing to, so I don't have coordinates. So this is a little different than how we started before. All right, okay. So what I'm going to talk about is probably the most common algorithm called classical MDS. To be an algorithm, I will explain the algorithm, and then I'll give some intuition, and then we'll go through an example of intuition of why this works, right? So, okay, the algorithm itself is only a few lines of code, so it'll be pretty easy to write up and understand what it is doing, and then we'll kind of go and break down why it's working. Okay, So let's look at this algorithm, classical MDS. Okay. And this is going to use, and remember our input is D, which is in our n by n. Okay, and what we're going to need is a centering cell matrix, Cn. Okay, so we're going to get this n by n centering matrix. Remember, this will move it so that if we apply this onto a data set, high-dimensional data set, it'll move it so all the coordinates are going to be 0. Okay. Okay. But we don't have that data set. We only have the distances. Okay. So the first step. So step 1, I'm actually going to square all distances, because we want to work with the squared distances. So I'm going to create a D2 matrix. Okay, I'm not doing D times D. It's defined. So D2, if I look at the coordinate ij, this is equal to dij, my original distance, this entry squared. So I'm squaring all the individual values. So now I have a matrix filled with the squared distances. Turns out because of the like Pythagorean theorem, such squared distances are going to be easier to work with here. Okay. Because of that, we're going to use an eigen decomposition, which kind of works on like the squared matrices instead of the original matrix. So we'll use that instead of an SV. Okay. So then step 2, I'm going to then do what's called double centering of this matrix. I'm going to create another matrix. It's going to be a -1/2 in front, which I'm not going to totally explain where that comes from, although the book derives it. I'm going to center D2, the distance squared matrix. And then I'm going to center it again on the right-hand side. Okay, so we're going to note that what this is really doing is this is kind of the transpose of the centering matrix, the second one here. Okay, so that's the right way to think about the second one. I can think about having a transpose here, but the centering matrix is its own transpose. Okay, so I don't need to write the transpose there. Okay, but I'm centering. I've kind of squared the elements, and I'm centering it on both sides. Okay, this is called double centering. I guess that should make sense. I'm doing centering twice, so it's double centering. Okay, then now this is then we need to, this matrix now kind of captures what we want, and we're going to do an eigen decomposition of this. So I'm going to get the eigen values and eigen vectors from the eigen decomposition of M. Okay, so we're going to think of, so kind of a hint of what's going on here is that M is going to be approximately look like a transpose here. Okay, so it's going to look kind of like a transpose after we've done this double centering. In fact, it's because I've done the double centering, it's kind of the centered version. So we're thinking we've somehow done like the centered version of the data, and it was kind of look like a tilde transpose. So that's why I did centering on both sides, and one was a kind of a transpose of it. And then I'm doing the eigen decomposition. Remember, the eigen decomposition of a transpose gives me kind of like the left singular vectors and the squared singular values, right? So the eigen values, these are the eigen values. These are kind of like the squared singular values. And the vectors here are going to be like the left singular vectors. And the left singular vectors they're not going to give me the average shape of the data, but they're going to give me kind of some coordinate in a new space for every data point, right? And now I want to embed the data points. So this is kind of what I want so far. And so we're going to conclude by getting the final thing is we're going to get our output. I'll say return. I'm going to get these new coordinates, right? I'm going to get these coordinates back here. Let's call, QI is going to be mu, this embedding map of PI, right? So the original data point, PI, I'm going to embed it. This is now going to live in RK. So QI, and the set I'm going to get back, the set I'm going to get, I'm going to call Q, right? So this will be a set of things, and I'm going to take the top left, the top K eigenvectors times the, and I'm going to scale them by the eigenvalues. And actually the eigenvalues, the square root of the eigenvalues, because those are like the squared singular values, right? So I take the square root of them again. L was like a diagonal matrix here, okay? And so this will be a set of points Q1, Q2, up to Qn, and these will live in Qk, right? Because this will be k-dimensional. I can think of these as having a k-dimensional basis here. I'm only taking Vk, this, this Vk matrix is going to be the top k eigenvectors, right? So this is going to be n by k, okay? And then Lk is going to be, I've zeroed out everything before, and I'm only going to keep this as a k by k matrix, right? So this will be lambda 1, lambda 2, up to lambda k, 0, 0. Okay? And so when I multiply, so this is just the Lk, or the Lk square root is just the scaling. And I'm multiplying that by the Vk vectors. One for each of the data points gives me k coordinates. And this will give me the embed. Okay, and this will be useful to kind of visualize these or get them in a low-dimensional space. And we'll see, for instance, if I embed these in 10 dimensions, I'll be able to run clustering on them, for instance, right? And we'll see that in the next set of lectures. Okay, so this is the algorithm. It's only a few lines of linear algebra, so not hard to implement, and that's why it became very popular method for this. Might be a little bit of a mystery of why this is working, what this is doing. Okay, we're going to go and kind of expand on the intuition by looking at kind of this matrix here, this way of thinking, and see where this comes from and why it makes sense to do something like this. If I had one of these A tildes, right, I could do a singular value decomposition or PCA on this after centering, right? Or if I had A tilde, I've centered it. I could do PCA on that, and I could get the top K of those things. That the embedding, that's exactly what is going on here in the third and the fourth step, right? But why does it make sense to do it in this case when I just have the distances, and why the squared distances? All right, so let me try and provide some intuition on this now, okay? And for those of you online, I can see the chat, so so you're welcome to ask questions. Why does classical MDS work? Okay, I'm going to give most of this intuition. Okay, and I want to start by this idea of instead of a distance matrix, let's say we had a similarity matrix. Okay, this would be a matrix S, which again would be an n by n, where each Sij is equals the similarity between this object pi and pj, where similarity is going to be larger. Things are more similar, meaning a larger value, they're closer together, right? So it's kind of the opposite of a distance matrix, right? If things are less similar, maybe their value goes to 0. And how am I going to capture this? So I'm going to think of I'm going to pretend there exists some A in n by d, some n data points in a d-dimensional space, right? Where this is A is equal to A1, A2, up to AN, right? These are the true data points in the space, and they give rise to this distance matrix or this sort of similarity matrix. Now, I don't have access to this, but I want to pretend that there was, okay? And then once I pretend that there was, the similarity, how similar are 2 points, this would then be captured as the dot product between AI and AJ. Okay? So I want to think of the similar as the dot product between them. Okay? It turns out that if that is the dot product, again, the dot product, if they're kind of pointing in the same direction from the origin and they're both unit vectors, it's 1 if they're the same, and it's 0 if they're orthogonal with each other, right? So this kind of should make sense. And when I get back to explaining how this relates to Euclidean distance, it should hopefully make even more sense. But I want to point out that this A transpose matrix, IJ, right, is exactly AI dot AJ, is exactly this dot product or the inner product in between the 2 points if I have the matrix A and J. Okay? This matrix multiplication between A and A transpose actually records in the ith j entry the dot product between them, right? So the similarity matrix, if I had this, I could do the eigendecomposition of this, and that would give me the embedding, exactly what I'm looking for. Okay? So this is great. So if I had this similarity matrix, this would be really good. But instead what I have is this squared distance matrix, where this is entry Aij is instead more like AJ squared, right? Let's say I wanted to use the Euclidean distance in this d-dimensional space I don't have, but I have this, right, instead. Okay. Well, if I wanted to get here to the dot product, I can expand this actually. The Euclidean distance, you can expand this the same way you would expand this for scalars. This turns out is equal to AI squared plus AJ norm squared minus 2 times the inner product AI AJ. Okay, this is standard expansion, okay, of a squared distance. Basically, the yeah. So if I just if this was instead scalar values and I expanded kind of a minus b quantity squared, it would be a squared plus b squared minus 2ab. Right? So that's the same thing here happening with Euclidean distance. I can write out this expansion. And importantly, the last term here is the inner product Aij. Okay? So that means that if I have the squared distance matrix, then I can solve for Ai Aj inner product. This is what I want to create this similarity matrix, which I can take the eigendecomposition of. This is equal to 1/2 AI squared plus AJ squared minus AI minus AJ quantity norm squared. Okay, so I can solve for this. Okay, so, and what's great is this has this this term, the squared distance in here, which I have. Okay. Unfortunately, I don't have these two terms, right? I don't have these two terms, so I can't. It seems like I can't quite get this similarity matrix. If I did, construct the similarity matrix, and then I can do eigen decomposition. But I can get these. I just have to just make a choice, right? So so I can solve for AI squared and AJ squared. Here, let me move
Mm-hmm.
I want to copy up from above. Remember, we had AI AJ. This is what I want. This is 1/2 AI squared plus AJ norm squared minus AI minus AJ squared. Okay, so I can solve for these, and we have and this one we know how to get already. Okay, so I can solve for these if I assume, let's say I assume that A1, I'm just going to arbitrarily pick the first data point, and I'm going to say that this is the origin. Okay, if I assume the first data point is the origin, okay, this is just arbitrarily the first one, well, then I know that A1's norm squared is equal to 0, and AI norm squared, well, this is equal to AI minus A1 norm squared, because A1 is all zeros, and this is equal to, in my distance matrix, squared distance matrix, I1. Right, so if I arbitrarily said I'm going to make the first data point at the origin, well, then I can pull these out of the squared distance matrix, right? I can pull these out of there, out of the squared distance matrix. And this means that I can solve for AI AJ equals 1/2 of D2, the entry I1 plus this squared distance matrix J1, assume that's going to be so symmetric, and this is, of course, this is a minus D2, this is just IJ, right? Okay, so this looks fairly similar to the form that we had on the previous slide, right? We have this form here, right? So this is the magic form that's going on here. And actually, I want to highlight, yeah, we have the minus 1/2 and the D2, right? That is kind of like the 1/2, the minus, and the D2, right? That's kind of giving me my AIJ, and if I do this for all the entries, it's going to give me this similarity matrix, which is basically A transpose, which I can take the eigen decomposition of. Okay, so this basically works, but I made some fairly arbitrary choice that that A1 is equal to the origin. So the difference with classical MDS, and I'm not going to kind of go through all of the math in this, but the main difference is it says instead of doing the first one as the origin, let's take the average. Let's do this on average over all of the data points. I'm going to do the average of these, assuming each of the data points is the origin, and kind of add up the average result I get. And it turns out that is equivalent to kind of applying these centering matrices. And I put the centering matrices on A and on the A transpose. And so I kind of get the A tilde transpose, the eigen decomposition. That will be the left singular vectors, which will give me the embedding I'm hoping for with MDS. Okay? So I'm not going to go through all those steps, but hopefully that kind of explains why this works. Why, if we had this similarity matrix instead of the distance matrix, it would be easy. But we're more likely to get the distance matrix, and then we have to do this double centering in order to get in order to get the kind of the embedding that makes sense and in a clean form to translate the distances into the inner products, which then give me my A transpose. Okay, great. So any questions on the algorithm? I'm going to go through an example in Python. Hopefully that might make things a little bit more clear. Again, this is linked off of the web page. This is kind of a small demo. Let's go through this demo here. We do this in NumPy in Collab. And we're given the input here is just a set of 5. There are 5 objects which we don't have, but we have all the distances between them, right? And you'll notice that the distance matrix so the diagonal of this is all zeros. The distance between something and itself is 0. That makes sense. And it's going to be symmetric. The distance between starting from 1, the third entry, and the first entry is the same as the first entry and the third one, right? 3 and 3. It's symmetric in that way. Okay. And then we're going to create this D2 matrix, which you can do by NP square. And this squares all the individual entries, right? So 8 became 64, 7 became 49. Okay, this was the first step. The second step is we need a centering matrix, right? So I made identity matrix minus 1/5, which is 0.2, times the all ones matrix. That's 5 by 5, and here's my centering matrix. And now I do double centering, right? The double centering is minus 1/2 times centering matrix, the D2 matrix, and the centering matrix again. Okay. This is going to give me my averaged similarity matrix. Okay. And now I just need to do the eigendecomposition, right? The eigendecomposition gives me L, which is the eigenvalues, starting about 5, or no, I guess that's about 52, about 8.1, and then they start getting strange. They start getting negative after that. Okay, so we'll use the top 2, right? And there's also these imaginary parts. Okay, when you do the eigendecomposition, it's not a perfect positive definite matrix, or there's some rounding error. The eigendecomposition might have some imaginary values to the eigenvalues. So we're going to take the real parts. Let's take the real parts, and also I'm going to take the square root, right? So I'm going to take them to a power of 0.5. That'll take the square root of them, and then I'll take the real part of what is left. Okay, and these will be kind of like the singular values. Okay, now we can see the singular values are about 7, 2.5. Remember, 7 was about square root of 52, right? 2.8 was about the square root of about 8, right? Okay, so that's what these values, and the rest of them are really, really small. Okay, so let's go see this V2 and S1, right? So this is the matrix. Oh yeah, so this is the S1, the S2 matrix, this singular values. I've taken the top 2 components here, and now I multiply them together to get Q. This gives me a representation of each of the data points. The first data point coordinate -3.3, -2.1, right? And the second one, -2.2, 1.6, right? We can plot them, easier to see, right? So now we plotted them. This gives an embedding of these data points. I haven't labeled them on here, but you can see from the above part when I write out Q, which one corresponds to which, right? So the distance between the first data point and the second data point. The first one is down the bottom left corner. The second one is -2 1.6. So it's -2, 1.6. It's the top one up here. Okay. The distance between those first two data points was supposed to be about 8, if I remember, right? No, it's supposed to be 4. The first and the second data point, the distance was supposed to be about 4. Let's see what we get. We go from about -2 to about 1.5, and we're going over about, from the y-coordinate, about 1. Yeah, so the distance is about 4. So we did pretty good, just a spot check. And you can look at the other ones, and you can see some of them were supposed to have a distance of closer to 7 or 8. Well, those are 2 data points over on the right here. Those points are 7 or 8 distance from all the data points on the left. So this actually works pretty well. Okay, and it's a pretty simple algorithm, and it kind of used the power of the stuff that we had done earlier, but in a kind of a more complicated way. So great. So this is what I hope to cover. Some people are online, so you can ask some questions, but otherwise we will wrap up the dimensionality reduction set of class, and we'll have a quiz as planned on Thursday. I'll go and reiterate this with announcements on Canvas. Sorry for the power outage if that affected you. All right, I will. Feel free to ask questions. Otherwise, I'm going to sign off.